great pleasure to welcome Bobby Gramacy, who's a professor of statistics at Virginia Tech, to our seminar. So Bobby works on applying statistical methodologies to engineering problems. One of his main tools is the Gaussian process, and he's going to talk about that today. So one unique feature about Bobby's work, he's very good at coding. And he develops packages as well as good and elegant methodologies. And his packages are also good and elegant and very useful. Actually, that's how I learned about his work, by hearing from one of the people who used the package that Bobby developed. So it's a unique combination of good software development skills and developing good methodology. So we're pleased to have you, Bobby, here today.
Thank you. Thanks very much for the nice introduction, and I'm glad to be here. And this recording experience is new for me, so I hope I don't ruin it for you. Okay, I'm going to talk to you today about Gaussian processes, and I'm going to tell you about work. So this is my postdoc, Mikhail, who's sitting in the front row here. I brought him up here with me so he could participate in some discussions later today. This is mostly his work. I have more experience at selling it. I'm more willing to exaggerate. So if you really want to find out how it works, you can talk to him later. So let me tell you about the setup here. I need to engage the web browser somehow. I have to move to the next. Okay, here we go. Maybe click. There we go. Perfect. All right, so I'm interested. A lot of my research is on computer simulation experiments. But if that's not something of interest to you, just think about regression problems from engineering if you want. So my computer experiments are often simulating real-world dynamics or solving complicated systems of equations, so they're computationally expensive. The generic setup is that there's a function f that maps a handful of inputs to a real valued output, and that function f requires a lot of computational machinery to evaluate. So there's interest in reducing the computational expense of evaluating the function f, and the way that we help do that is through statistical modeling. So in the literature, people talk about surrogate modeling or emulation. That's just the enterprise of fitting a statistical model, a statistical response surface model, to pairs of x, y coordinates. The x's are the inputs to the computer code, and the y's are the outputs. Historically, the outputs were deterministic, and that was a unique feature of the computer models that people were exploring, particularly in the 90s and 2000s. But these days, stochastic simulation is a big deal, which is mostly what I'm going to talk to you about today. So the idea is to fit a statistical model to the x's and y's that come from your computer experiment, and then use that model in lieu of new expensive simulations in order to understand something about the system. Maybe you want to figure out which inputs are driving variability in the outputs. Maybe you want to optimize, find the inputs that minimize the output of the computer model, and so on. The model that's percolated to the top over the years for these regression problems is the Gaussian process. And the Gaussian process makes it sound fancier than it is, but really it is a pretty simple thing. It means model with multivariate normal distributions. So model the outputs y as a function of the inputs x through a distance function, or an inverse distance function, that defines the covariance structure. Why do people like that? Because it makes very accurate predictions, as I'm going to demonstrate to you, and they have good uncertainty properties, especially in the case when the computer model is deterministic. They'll reproduce the data at the inputs that have already been run, and they'll give you uncertainty quantification at novel inputs where you've never run the computer experiment. So over the next few slides, I want to do a little bit of review. I always like to make my talks appeal to people who don't know a lot about the area, at least at first, and then I'll try to show you some fancier things by the end. I don't know if you want to know this, but it looks great on the screen, Vadim, but in your video capture, I think it's being cut off on the edges. Okay. All right, so I want to show you what it means to put a Gaussian process prior on regression functions. So to generate random functions from a Gaussian process, here's what you do. I'm describing it in words, and I'm giving it to you in code. There's going to be math in this talk, and there's going to be code in this talk, and neither of them should be scrutinized. The intention is not for you to follow the math or the code, but it's supposed to make you feel comfortable. There's some good math behind the stuff, and there's some code that does it, and the code's not complicated, and the talk is generated. All the figures and the outputs in this talk, well, not all of it, most of it, is generated on the fly, so this is a reproducible presentation. Okay, so here's how you generate random functions from a Gaussian process prior. Take a bunch of inputs, maybe a grid in the input space, and then build a covariance structure based on pairwise distances between those inputs. I'm using the correlation function from the previous slide, except for some simplifications, some simple values of the parameters that were in that function. So you calculate the pairwise distances, you e to the minus that distance, that defines your covariance structure, and then you put that covariance structure into your favorite multivariate normal random generating function. So that's my code here. I have a grid of x's, I calculate their pairwise distances, and then I build a covariance matrix, and then I take 3 random draws from that multivariate normal distribution. Perfect, thank you. So there's 3 random draws from a multivariate normal distribution. So that's a prior over functions. It generates random functions. In this case, there's 1 input and 1 output. So each of those lines is a random function generated from a Gaussian process prior. Of course, we're not interested in generating random functions. What we want to know is which random functions support the data that we've collected on this computer experiment. So which ones are like the x's and y's that we have in our data. So we want to do some learning. If I just showed you how to generate random functions, I could call that a prior. And what I really want is the posterior over random functions given the data, given the xy pairs that I have. So that's a Bayesian interpretation. But you don't need to be a Bayesian to do the calculations. In fact, all of Gaussian process regression boils down, all of it, 99% of it, but boils down to identities for conditional distributions of Gaussians. So you could Wikipedia or you could Google Wikipedia conditional distributions of a joint multivariate normal, and what you get is that link, and you could actually click on that link and go there, but I'm not going to. I've given to you what Wikipedia says on that page. It says that if you have a joint Gaussian vector with components x1 and x2, then you can get the conditional distribution of x1 given x2 from the mean vector and covariance matrix that define the multivariate normal. So we're just going to apply that to our regression setting. So Gaussian process prediction is just a special case, an application of those conditioning rules. And in fact, most Gaussian process implementations simplify even further by assuming that the mean of the multivariate normal is 0. So I don't even need to worry about the mean part of the multivariate normal distribution. So my application of those conditioning rules is shown on this slide, giving us a function of x determining the y value conditional on xy pairs that I've modeled as multivariate normal. These equations were first presented in a regression context in this way back in the 60s in the spatial statistics literature, the geostatistics literature, and it's been called Creeking ever since then. But in the computer modeling literature, we don't tend to use that term. We just say Gaussian process prediction or whatever. In fact, you can do a little theory on it and show that those equations describe the best linear unbiased predictor. And it's a linear prediction. You can see that because I've got a linear equation in the output variables y. So how does it work? Let me demonstrate it for you in code. Suppose I have some super simple data. I'm going to use a sinusoid to stand in for my computer simulator. So it's not a real computer simulator, but it lets me give a nice illustration. And I've evaluated that computer simulator at 8 inputs uniformly distributed from 0 to 2 pi. And then I'm going to do the calculations right in front of your eyes that calculate the pairwise distances. That's the distance function here. Then exponentiate the negative of those distances. And I also need the distances between some predictive locations, some out-of-sample testing locations, and the input data locations. And I need to exponentiate those as well. And once I have all of those distances or inverse distances calculated, I can solve the linear systems in order to make my conditional multivariate normal to calculate my posterior predictive distribution. So I have my linear predictor that's called mu p, my predictive mean, and my covariance matrix that's called sigma p, so my predictive covariance. And once I have the mean vector and covariance matrix, I can then simulate random draws in exactly the same way with my favorite multivariate normal generator. But those random draws won't just be from any functions. They'll be from functions that well support the data on which they were trained. And it's kind of miraculous how well it works. I'm going to show you those functions on the next slide. And I'm also going to summarize their distribution for you, their upper and lower 95% quantiles. So here's what they look like. So each gray line is a random realization from the posterior distribution. So that's the Gaussian process prior combined with XY data gives me the Gaussian process posterior. It's a random variable. It's random functions. And each gray line is a simulation of one of those random functions from that distribution. The black line is the average of those gray lines. It's the mean of my multivariate normal distribution. And the red lines were those quantiles that I calculated right at the very end. And you can see why people would like this for computer simulations, especially for deterministic ones, because it interpolates and it gives you sensible uncertainty quantification away from the locations in the data that were used to create the y values, away from the x's in the training data. They give nice football-shaped error bars. So that's a very simple example. Typically, people define their correlation structures in a little bit more fancy way. So rather than just doing e to the minus Euclidean distance, they parameterize rates of decay of correlations differentially in different input directions, and they also allow noise in the data by breaking the continuity of the covariance structure in the input space. So I've written down the same correlation function that I put on my first slide here again at the top on my 12th slide as a function of some unknown parameters, theta and tau squared and nu. How would you do inference for those parameters? In the usual statistical way. You could do cross-validation, you could do method of moments, you could do whatever. I like the likelihood, so I'm going to use the multivariate normal distribution to define a likelihood, take its log, and then take its derivative and do calculations in order to maximize. So I'm showing you the log likelihood here. It's just the log likelihood of a multivariate normal data generating mechanism. And I have 3 sets of unknown parameters. One of them I can solve the likelihood equations directly. So I can differentiate with respect to the scale parameter, which I'm calling nu, and set it equal to 0 and get a solution that looks like a residual sum of squares, like from an ordinary linear regression. The other parameters take a little bit more work. So if you plug in that estimated scale parameter and write down what's called the concentrated log likelihood as a function of the remaining parameters, you have a little bit more of a challenge in order to solve for the maximum likelihood estimates of those parameters. You can calculate the gradient with respect to those parameters in closed form, but you can't solve on pen and paper. You have to use a numerical method.
Excuse me.
Yeah.
Is there a reason that you cannot solve these numerically?
The reason I can't do it is that I'm not a good enough mathematician. No, that's just a joke. I think it's just that it's not algebraic. It's not easy to get the right-hand side and left-hand side to work. I mean,
But then you can have a target function and the first derivatives you can do some kind of mathematics.
oh, that's what I'm going to do. So numerical methods are pretty good. I just can't do it on pen and paper.
Oh, okay.
Yeah.
Okay, that's what.
Yeah. So here, I'm going to do it for you. I'm going to write down the negative log likelihood. NL is my coding of the negative log likelihood, and GNL is my gradient function for the negative log likelihood. And then I'm going to put that into an optimizer. So this is the most code I'm ever going to show you on a slide, and I don't want you to go through it, but it's really not that bad. What is that? 15 or 20 lines of code, and I can stick those 2 functions into a numerical optimizer, and the solutions come pretty quickly. And I'll do that for you in an example. So I'm going to do a second example. I'm going to bring up the input dimension a little bit to stress it. 2 dimensions is not very big. We can do bigger than that, but just to make a simple example where visualization is straightforward, let me generate some toy 2-dimensional data. So the response function here, y is a function of x1 and x2 through this exponential and quadratic and so on. I'm going to use that to generate data. So I have 40 input-output pairs, 40 xy pairs, and then I stick my negative log likelihood and gradient into the optim function in R, which does numerical optimization. I'm telling it to use BFGS, which is my favorite local optimization method. And it comes back and gives me estimates of the 3 unknown parameters. So the first one here is the rate of decay of correlation in the first coordinate in the input space. The second parameter is the rate of decay of correlation in the second input. I put the first one's about 2 times longer than the second one, but this is all based on random data. This time it was more than 2 times longer than the second one, so I never know what's going to come up. Yeah?
So just a question, you mentioned normally you do that by cross
Sure. Yeah. You could put priors on these parameters, which would regularize them, which would prevent that a little bit. Yeah, there's always the danger of overfitting. I mean, there's only 3 unknown parameters and 40 data points, so it'd be difficult to overfit with this particular setup, but I could add more parameters and then optimize more of the noise, and then I would definitely be overfitting.
You just use like basically radial basis function interpolation, and basically for each point you can optimize the sigma, the
Yep.
variance.
Yep.
Basically what gets spiced at each point.
Yep.
So
Yeah, so I am avoiding doing that because I have many fewer degrees of freedom than this radial basis function idea that you're talking about. But there is a deep connection between Gaussian processes and radial basis functions. And in the way that I've set it up, I've strongly regularized that system if you're making that connection.
So what type of priors would you use?
Oh, for this setup, I don't think priors are actually necessary. But you could put an exponential prior on the length scale parameters that would, yeah. Okay, so now that I've estimated the unknown hyperparameters, I can cut and paste the code I've shown you before that rebuilds the covariance matrix with those parameters and recalculates the distances to testing locations under those parameters, and then follows the same set of multivariate normal conditioning rules that I showed you from Wikipedia. And those are right at the bottom here. So my same mean function, linear function of y, same covariance matrix. In 2 dimensions, it's harder for me to show you all of the sample realizations. In 1D, that's easier. In 2D, that's harder. So I'm just going to show you the mean surface and the standard deviation surface. And that's what is on this next slide. So I have learned that the function is bumpy. It's got a down trough and an up trough near the origin, actually, and that it's relatively flat away from that location. So the left-hand plot is a perspective plot on the mean surface, and the right-hand plot is a heat map of the variance surface. It's actually the standard deviation surface. So the standard deviation is lowest nearby where I have training data. The training data are my open circles, and higher away from where I have training data, which makes sense. It's got that football shape, but now it's a little bit harder to see the footballs in 2 dimensions. All right, so that's great. Where do we go from here? That's my Gaussian process review. Increasingly, data exhibit all sorts of wily properties, and we are getting very ambitious with our computer simulation experiments with individual-based models and other stochastic simulations that create very low signal-to-noise ratios and that also have input-dependent variance, where not only is the mean changing over the input space, but so is the variability changing over the input space. So I'm going to take you through both of those 2 things with some of my contributions to this literature. We'll start first with low signal to noise, and then we'll move to changing signal to noise over the input space. So my little setup sentences here: with noisy processes, more data sampling is necessary to separate signal from noise. That's sort of basic stats, right? More noise, the more data you need to estimate means and stuff like that, right? But Gaussian processes don't do well with big data sets. So they're great, they smooth, they give nice uncertainty quantification, but whenever you're working with a multivariate normal whose number of coordinates is increasing with the data size, so we have an n-squared covariance matrix for n input locations, we have to decompose that matrix to invert it, to calculate its determinant in order to work with that in the multivariate normal. That means n cubed calculation, which means that n these days can maybe be as big as 10,000. Unless you're willing to go to some kind of sparse covariance matrix setup, which don't work that well in that literature. So what can be done? Replication, which is what separates signal from noise, also gives nice simplifications to the Gaussian process calculations. So replication is a powerful device for separating signal from noise, and it turns out that it will give you computational savings as well. The first steps in this area showed great promise about 10 years ago. So a method that I'm calling Stochastic Creeking, they basically said what you should do is have lots of replicates. What's a replicate? A replicate means rather than more unique spatial locations, I have many observations of y at each location. So I'm replicating those inputs when I'm observing those outputs. Rather than working with all that data, just take point-wise averages and point-wise variance calculations. So use a method of moments estimator to estimate the mean at each input location from the multitude of replicates there, and the variance at each input location from the multitude of replicates there. And then rather than work with the full data, work with those values instead. Yeah?
Yeah, I just have a clarification question. So you can do this, I mean, like to generate like whatever the data you want because you're doing computer simulation, right?
Right.
So you can just so trying to like change your like process a little bit and generate data. I mean, like you want to get it
Right.
So my understanding is correct.
Yep.
Thanks.
Yep. We are definitely working with designed experiments. If it's observational data and it turns out that you don't have any natural replication in that observational data, then you may not be able to apply these techniques. That's right. So I'm just notating here y I bar and sigma I squared hat. Those are my reduction of a big data set down into the parts that are unique to the unique input locations. And then it turns out that you can apply the same predictive equations that I just showed you a few slides back with that data instead, and it has a lot of nice properties. In fact, you can show that it gives you a best linear unbiased predictor, but it's an asymptotically best linear unbiased predictor, and it involves an expectation. There are some drawbacks to this. Independent moment-based estimates of variance in particular has its drawbacks. So this is an old method, not a new method. We figured out that a very common linear algebra trick, a set of identities that gets used a lot in spatial stats and in computer experiments, but has never been used in this way. The Woodberry formula allows you to do the stochastic Creeking idea that I just showed you without any asymptotics. So you can make an identity that maps a big data set under replication to calculations that just involve the unique locations and that also involve averages and other things. So these are the Woodberry identities. You could Wikipedia that too, but you'd have to do 2 different Wikipedias to get the 2 different formulas, so I didn't provide a link for it. So these are the Woodberry identities that show you how to decompose matrices that have a certain structure in order to get their inverse and determinant. So I'm going to apply those with our covariance matrices, and I'm going to do it in code first, just to sort of show you what's going on here. So here's some code to help illustrate a map from a small number of unique locations mapping many replicates in a full data set. So there's 50 unique locations, and there's a replication factor of approximately 3. But some inputs are replicated more times than others. So I'm not going to go through the code for this. The whole point of the code is to set up the plot that's on the next slide, which I think is very visual. So I'm going to skip to that and just show you the plot on the next slide. So I'm visualizing the mapping here from a small little n by little n covariance matrix. In fact, it's 50 by 50. So there's 50 here and 50 there. So it's a 50 by 50 matrix together with a sparse matrix U. So the matrix U only has 50 non-zero elements in it that are shown kind of along that diagonalish thing there. And those 2 things combined through the Woodberry formulas map out a big N by big N matrix, which is shown on the right-hand side. That's 150 by 150. So it turns out that we can work with this, using that, to do calculations that you would have calculated on the big data set. And there's no approximating going on here. Everything is fully unapproximate.
So U represents the replications?
Yeah, actually the numbers that are in this matrix are giving us. Actually, that's not quite right. The numbers on the diagonal of this matrix are keeping track of the numbers of replicates.
So what is the meaning of U? Trying to get the equation.
So the idea of U is that it's U and V in this formula.
Okay.
So U is equal to V transpose, and that's where it's coming. And D is our K, and so that's the basic idea. All right, so there's the picture. It turns out that if you work carefully through the predictive equations of a Gaussian process through these identities, so the map between stochastic Creeking and what I was showing you at the beginning of the talk is in the very first displayed equation there. Using that mapping between these 2 worlds, I can get predictive equations that are shown in the middle set here that give you an identity between big N calculations and little n calculations. So look at everything on the left-hand side has a big N subscript, and everything on the right-hand side has a little n subscript, which means I can calculate the big N things working with only little n of them. Why is that useful? Because the calculations for the right-hand side are only order little n cubed, and 50 cubed is a lot smaller than 150 cubed. So we can get very fast and accurate predictions that involve no approximation. So let me say one more thing about that. Not only can you do it with the predictive equations, you can also do the same trick with the log likelihood and with its derivatives. So you can maximize the likelihood to get settings of unknown parameters with thrifty equations that are not approximate, which has never been possible previously. Let me illustrate to you the computational savings to show you what it potentially could be. So I'm going to revisit our two-dimensional problem from earlier. I'm going to set up the data so that there are 100 unique input locations, but the response is observed under lots of replication. So each of the unique 100 input locations is going to be replicated from 1 to 50 times randomly, so that on average each location is replicated 25 times. So there's 2,500 is what my big N is. My little n is 100, and my big N is about 2,500. I'm going to load one of my software libraries to do the calculations, because it's more than a page of code to do this. So we've got a nice R package called Het GP. I'll explain what the Het part means in just a little bit. That will allow us to make a comparison between big N calculation and little n calculation. So the big N calculation, that is, if you do things the old way, it takes 348 seconds to develop predictions with maximum likelihood inference at a set of testing locations. If you do it the new way, it takes 1/10 of a second. So that's what, 3,000 times faster? So 3,000 times faster using this linear algebra trick than not. And I get exactly the same estimates of the hyperparameters, up to 6 or 7 significant figures. Okay, so replication, huge. Why? For two reasons. Because it makes the calculations faster, and because it separates signal from noise. Now I'm going to make the problem harder and make the noise change over the input space. Gaussian processes do not do well when the noise is changing over the input space. Here's a very simple example from the literature. This is called the motorcycle accident data. It's actually a computer simulation experiment. It simulates the acceleration of the helmet of a motorcycle rider before and after an impact. So the impact here is at time 12 or something like that. So there's very little acceleration, and then there's an impact, and then there's a whiplash effect. And there's not only changing mean, but changing variance in the observations. So my fit there is just an ordinary Gaussian process fit in terms of the mean function as a solid red line, and a variance function shown through the quantiles of that distribution as a dashed line. So I'm going to make sure I'm doing great. I've gone through 30 slides in 30 minutes. I'm perfect. Okay, so it doesn't do well. Why doesn't it do well? Well, the variance that it estimates is way too high in the early regime. It looks okay in the middle regime, but then I think, again, it's too high in the final regime. So there's some regime changing of variance going on, and I'm not capturing that with my Gaussian process fit. Now, stochastic Creeking was developed for the same two reasons that we're developing our methodology. One is lots of replication, and we want to deal with that more efficiently. And another is to track input-dependent variance. It turns out that this independent moment-based estimate of working with the data does allow you a certain amount of heteroskedastic flexibility. Think about that for just a second. Independence allows you to measure different things in different locations, right? It's the extreme of measuring different things in different locations. It says there's no relationship over the spatial field, therefore I can get the variances higher in one location and lower in another one. But I lack the ability to smooth between them because I've created an independent structure. The way that the authors of the Stochastic Creeking paper suggested to deal with that was to, after the fact, try and smooth the variances with a second Gaussian process, which is a good idea. In fact, the machine learning community 10 years earlier suggested that that's what you should do. And in fact, they went even further to create a link between the mean surface and the variance surface through a set of latent variables. So back in the late 90s, a paper in NIPS, which is a machine learning literature, they wrote this, like MCMC was a big deal in the late 90s, and they're like, if you set up this Bayesian hierarchical model and do MCMC with all these latent variables, then you can estimate means and variances at the same time. That was the gist of that paper, and you could do it with coupled Gaussian processes, a Gaussian process for the mean and a Gaussian process from the variance. The overall method, however, is really, really slow. It's not n cubed, it's n to the 4, actually. And then you've got a factor t, which is the number of MCMC iterations. So the result is a method that's totally impractical for all but the very smallest data sets. For small data sets, it works great. It does the right thing. It gets you smooth means and smooth variances, and it looks great. But more than 100 points, forget about it. The key ingredient, though, is the idea of introducing a latent variable to describe the variance is workable. I think it's workable within an optimization framework if you at the same time take into account the savings that you get in calculations from replication being in your design. And they didn't think to do that. So the key ingredient of having a latent variance under a Gaussian process prior, which can be smoothed, what am I writing here in this equation? I'm saying that some deltas, which I'm going to think of as my variance over the input space, is going to have a Gaussian process prior. It's going to be multivariate normal with a certain covariance structure, and then I'm going to be able to smooth it through some best linear unbiased predictor. Again, the point isn't to stare at the mathematics and understand it, but take a few steps back and say, oh, he's just doing a Gaussian process prior on variances. And then you can make a nice connection by defining delta and lambda in certain ways to get the previous independent setup on the one hand and a nice smooth setup on the other. So it kind of bridges the gap between independence and smoothness. And rather than a full MCMC to learn what these latent variables are, it turns out that you can do a lot of calculation analytically. You can write down a log likelihood for all of the unknown parameters, parameters to the covariance structures for both Gaussian processes, the latent variables that you're using to describe the variance. All of it you can write a log likelihood down for, and you can differentiate it in closed form on pen and paper, and you can put it into your favorite optimizer and solve. So in other words, you can like sort of squish it into this optimization framework, which is more or less identical to the one that I used at the very beginning of the talk to show you how we estimate unknown parameters. So those are the calculations that are involved in that. I'm going to show you how it works with a library that we developed. So our library, again, is called Het GP for heteroskedastic Gaussian processes. And it does the two things I've been telling you about at once. It handles replication efficiently, and it learns variances along with means. And for this motorcycle data, it can do so in about 3.5 seconds. And that's on my laptop, which is over there, which I compiled this talk on. Yep.
So just a question. So this is a Gaussian process. Is that the natural prior for variances? Just because the
Nope.
range,
Sure. So I skipped over it. Alternatively, the log of the variances could be modeled in exactly the same way. So if you were concerned about negativity or something, you could work with log variance, give it a Gaussian process prior, and then every time you use that latent variable in your calculations, you first would need to exponentiate it. So that would solve the very first objection that people have to Gaussianity. That also creates a multiplicative error structure, which may not be appropriate for your data. So we are kind of trying to find a hammer for all our nails, right? It's not the ideal thing, but it does many of the important things.
I mean, I don't know the literature well, but there's a basically different prior or different process for variances.
Oh, you could, people talk about gamma processes. Okay. That would be appropriate. The thing is that the gamma distributions afford a lot less analytical tractability. Okay. So Gaussians are nice because people can do a lot of calculations by hand. So we are fitting what is it, a square peg into a round hole? Is that the? We are kind of doing that, but we're doing it because we can do a lot more of the calculations in closed form. Okay, so I can learn all of these variances, and I can do it relatively quickly, and I can make a prediction. And now I can show you on the next slide what this heteroskedastic Gaussian process fit would look like on the motorcycle data. And this is what it looks like. Okay, so my fit is on the left, and on the right, I'm specifically showing you the variance process. So the variance starts low, goes high, and goes back low again. The green dots are the observed variances in the data. So it turns out that some of the inputs are replicated, and since they're replicated, we can get a notion of variance. If you don't have replicates, you get no notion of variance, right? You have a 0 in the denominator of your variance calculation. So the green dots are the observed variances, and you can see that I'm definitely smoothing them, right? I've got no observed variances out here, even though I observe data out there. So smoothing is essential out on the left, and then it's very diverse here on the right. It's going up a bit, but there are some low observed variances. So it's taking a compromise between those and doing a nice job, I think. Yeah?
What's the sample size of the real data set?
131. And there's about 100 unique locations. Okay, we have a real example that this is not a table that was generated by code in real time because it's a huge Monte Carlo experiment with many repetitions, and it takes a while to generate. But this is on an 8-dimensional problem from the literature, from the optimization literature actually, called the assemble to order problem. And it is heteroskedastic. If the basic setup of the problem is that you have an inventory, and the optimization is over how many items you keep in inventory. If you have a lot of items in inventory, you can always fulfill your request to build products, but it's expensive for you. So you have very low variance because you can always build the products. You never need to wait for anything when demand comes in. However, if you have very few items in inventory, if you're cavalier about that, then you may not have all the items you need to build a product when the request comes in, so you make your customers wait, and which means you can't make money, and so on. And you can imagine how mean and variance are linked there. There's a risk-reward trade-off. Right? If you have less items in inventory, it costs you less money. You have the potential to make more product, but if you can't fulfill orders, then you're not able to make money. So there's a mean variance trade-off going on there. Anyway, I'm not going to go through every row and every column in this table. Our methods are the red methods. Higher numbers are better, and our methods are higher. This is being measured by what's called a proper scoring rule that takes mean and variance into account. One problem with our methods, though, which are on the right on this table, is that they're a little bit slow. So they take some time. They don't take as much time as you working with all the data without replication, but they take some time. So the latter part of the talk here is going to be about creating designs that give us a simultaneous ability to learn variance and mean over the input space, and that also keep computational costs down. Okay, so the last bit here is about time and about design. In these models, in these non-parametric models, it makes very little sense to create your design in advance. That's the way that most people would tell you to do it. Create a big design of size n and then run your experiment. That doesn't work really well for non-parametric methods. It's much better to learn a little bit, create a slightly bigger design, learn a little bit more, create a slightly bigger design. So that's the framework that we're going to work in. In fact, we're going to add, our framework is going to be kind of one point at a time. I have some data. I fit a model like our heteroskedastic Gaussian process model. I use that fit to optimize the criteria to choose the next input location. And then I evaluate the response to that input location, which grows my design size by 1. And then I repeat in that way. So that's the basic setup. There are many criteria that you can optimize in this framework. We're not going to be exhaustive about that. We're going to use a very common one that involves predictive uncertainty. So we're going to measure the quality of our fit in the input space by an integrated variance calculation. So we want to average the variance over the input space, and we want that average variance to go down as we add more samples. So it's just the integral of sigma squared over an input domain. And it turns out that this integral is computationally tractable. There are many versions of it in the literature. I'm giving you one here. Again, the point isn't to scrutinize it, but just to show you that there are calculations. And the ones that we prefer are very nice when you're just looking to add one more point. They're nice for the same reasons that other things have been nice in the previous slides. We can take their derivative and we can optimize them, and we can do all that in closed form. Well, the optimization is numerical, but the derivative's in closed form. All right, let me give you an illustration of how our sequential design thinking works. This picture shows two different potential estimates of variance over the input space. So the blue line is a prediction of variance, and the green line is a prediction of variance. And as kind of an anchor, we've made these lines go through the red dots, which represent actual observations of variance. Suppose we had those. Right? It's just a cartoon example. So at five input locations, I've observed what the variance is, but I haven't observed the variance at other input locations, and the two lines are two different guesses as to what they might be. So the integrated mean square prediction error criteria says, integrate these variances. In particular, integrate them as a function of one new input location, so I can see which new input location would minimize those integrals. Okay, so I'm going to code up the integrated mean square prediction error criteria so I can evaluate it at a grid of potential input locations. So this is my coding of the IMSPE, and then I'm just going to evaluate that for my two different variance functions. I had two different ones. They're going to give me different IMSPEs, and then I'm going to see which are the best ones to choose in this little exercise. Okay. So this is the same x values, but different y values on this plot. The y values are now the criteria that I'm trying to optimize, which is a function of variance. In fact, a variance integrated over the input space. And what you can see, we want to minimize IMSPE, so the minimums are what we're after. The blue variance surface would recommend choosing the next input location to explore. It is not at one of the existing inputs. The green variance surface says, actually what I want is a replicate. I want to observe what y is at a location where I already have other y's. So the two different guesses as to what the variance surface is give two very different recommendations. One says explore, and the other says replicate, which is what I said that this talk was going to be about. It turns out you can derive a criteria where replication will always be preferred. So if your true variance function is bigger than that thing on the right, then what you're going to choose when you optimize is going to be a replicate. And I can code up that thing. This 6 lines of code is my implementation of that linear algebra. Again, no point in scrutinizing it. And I did that so I can plot it for you on the same axes as the previous set of plots. So the gray dashed line is where that function is equal. And then everything above that gray line, if all of the variance function is above the gray line, then you will replicate. So the green function, the green variance is everywhere above that dashed line, so the best solution is at a replicate. The blue variance surface has part of its function below that gray line, so we don't replicate. So there are situations in which you would naturally prefer replication, especially when the input-output relationship is heteroskedastic, especially when the variance is changing, which I don't think people knew before. There was some intuition about that, but there was never a result that was shown. Okay, so let me summarize again. What do we know? We know that replication is good from a computation perspective. It makes things faster. It's also preferred under integrated mean square prediction error when the variance is changing. So those are two good things, right? Faster and more accurate. It's not very often that you get both of those two things at the same time. And intuitively, it helps separate signal from noise, which might be the reason why the second bullet is what it is. So IMSPE is great, and replication is great. One downside to IMSPE is that it's, at least the way that we're applying it, is that it's myopic. We are doing a very greedy search. If we optimize the IMSPE each time and never look into the future to what those decisions are actually implying down the road, then we may not be doing an optimal thing from a long arc of the sequential design perspective. Searching over all of the things that you could do in the future is really, really difficult, though. Dynamic programming is involved, stochastic dynamic programming maybe even, and then you're in a realm where the computation is huge again. And we don't want to be in that realm. We have, however, found that we can look ahead a bit not in an exhaustive way, but we can look ahead over replication. And what I mean by that is we could acknowledge how our decisions now will be used to replicate in the future. And we can also look at how replication now can be used to impact future exploration decisions. So we can, in a limited sense, look ahead. And we can do it very quickly. So here's a little diagram of our less greedy, less myopic look-ahead procedure. So the red arrows represent choosing a new design. And the question is, do I choose a new design now at the very top of the pyramid? Or do I replicate now and choose a new design later? And how many times do I allow it to replicate first before choosing a new location? Or how many times do I consider replicating after I choose a new location? It's a big tree diagram. And I can look down into the future. The future is lower on this plot. As much as I want, it's just a little bit more computation to do it, to do more steps into the future. It's not a huge amount more replication. It's a quadratic function of the look-ahead horizon. So let me give you an example of how this might work in code. So here's a test function. It's a one-dimensional one just because it's easy to look at. And you can see that it has high variance in some regions and low variance in others. And the mean is changing too. Okay, so the question is, when we build these designs, potentially with some look ahead to help evaluate our criteria, what do the designs end up looking like? So this picture is the truth before we've observed any data. I'm going to do it all in code for you. Again, the point isn't to follow the code, but just to show you that it's not hard and it's there. So what's the program here? We start out with a small space-filling design. So at the top here, I've got x is a sequence from 0 to 1 of length 10. So I'm evaluating at 10 locations uniformly, no replication at all. And then I fit my model, my MLE Het GP, and then I evaluate my criteria, IMSPE n steps ahead with a horizon of 3. And then I augment the design to include that new location. So the very last one here is my choice. And you can see that it duplicates one of my previous locations. So I've actually chosen to replicate one of my 10 inputs. And then I incorporate that new data in, and we have an update function that updates the fit based on just the one new location. So I don't retrain things all the way from scratch. I just do a quick update. And then the idea is to repeat that over and over and over again. Keep getting designs that way. So I've just wrapped that code up in a for loop. I put it up to 489 so that the total design size would be 500. Okay. So I've got the fitting part, and then, IMSPE, new location, fit. IMSPE, new location, fit. Periodically, we restart the fit from scratch, just to make sure we don't get stuck in a local minimum of the likelihood surface. And once that's done, I can gather a final prediction on a predictive grid and show you what it looks like. And here's what it looks like. So the points are all of the data locations I've chosen. The gray bars are a visual aid to show you how many times those locations are replicated. So the location here on the edge was replicated many times. The locations here where the variance is low were not replicated as many times. But notice that there's replication everywhere. There's not just replication where the variance is high. There's also replication where the variance is low. There's more replication where the variance is high, and there are more unique locations where the variance is high.
Can you control that? Can you control the height of the gray bar?
In an indirect way. I can force more look ahead, and more look ahead, since it's only looking ahead over replications, will bias us towards replication. So I can control it in a loose sense. If I know I really want to replicate, I could force that. But I'm not sure that's exactly what you mean.
Well, it seems like we're replicating too much in the narrow areas.
Maybe.
You know what I'm saying?
Yeah, maybe.
Yeah.
Mm-hmm. So here's a question that maybe is similar to what you're thinking about. We have this tuning parameter now that governs how much look ahead we do. And the more look ahead we do, the more replication we'll get. So how do we choose that parameter? We have two schemes for doing that. One we call target, and the other we call adapt. Target is purely computationally biased. The goal is to minimize the n cubed calculations to encourage replication. And so it targets a ratio between big N and little n. That's what it does. Adapt is like, give me the very best predictive results, which is usually what you want, but sometimes you want to manage computation more than accuracy. And I won't go into the details of this one because it's too much math. We have a scheme that does it, and I'll show you the results. So here's that problem where we are considering many different horizons. So each of the first 6 plots, 1, 2, 3, 4, 5, 6, are just running the method for fixed horizons, starting from a horizon that we call -1, which is a special case of horizon 0, which is the default, and then 1, 2, 3, and 4. What you can see is that when the horizon is low, you have no replication pretty much. When the horizon is high, you have lots and lots of replication. The resolution is not fantastic, but you can see here that there are very few locations where replicates are being chosen. The out-of-sample accuracy, as measured by root mean square prediction error, is shown in the heading of each plot. You can see that that's going down, which is surprising. It's highest here, and it's lowest here. Here. It is lower there, but that's not one of the fixed horizon techniques.
It's the same number of functional relations in all 6.
Yes, exactly the same number in all 6. So the adaptive and target heuristics are also encouraging lots of replication. Target had a target of 20%, and it hit that exactly for its amount of replication, almost exactly. And its RMSPE is not maybe as good as some of the best methods. Those methods don't replicate as much. The adaptive one, which targets the most accurate predictions, has a reasonably high degree of replication and has the very best RMSE of any of the methods on the screen. All right, I will finish up in the next 2 minutes, let's see, with a couple of real examples. Okay. One of them is new, I haven't shown you yet, comes from Epidemic Management. So we have Stochastic Simulator that works with an underlying SIR model, a susceptible, infected, recovered model that involves some Markov dynamics and so on. The details are really not for this talk. It's just a 2-dimensional input space, and mean is linked to variance because the severity of the epidemic and its variability are tightly linked. If there's a high chance of a big outbreak, then a lot of people are going to die, but there's some chance that it'll die out, so the variance is high too. When there's not very many infecteds, there's a low mean and a low variance at the same time. So I'll just show you some pictures how it turns out. This is 2 versions of the 2D input space, and the heat map is showing you variance, not mean. So variance is high on the right-hand side and low on the left-hand side. And the numbers that are showing you how many replicates were chosen. So this is horizon 1, and the other one's adaptive horizon, which is trying to do the optimal thing. And notice on both of them that in the red region there are lots of replicates, more than in the yellow region. In particular, in the adapt slide, if you look closely, you can see there's a 54 here. There was one location that was replicated 54 times compared to 1s and 2s that are in other parts of the input space. So we are finding that replication is useful on this problem in order to learn what the variance is. How good are we at predicting? This is showing you our predictive error, our root mean square prediction error, as a function of design size. And almost everything that we do that I've shown you today, it does a great job of driving down predictive uncertainty. If you have very few inputs, then you have very high error, but you very quickly learn what's going on. The box plots on the right are showing you the distribution of RMSEs in a Monte Carlo experiment at the very end, at time 500. The left-hand plot's just showing you averages, but I wanted to show you some of the variability, and the best way I thought to do that was with the box plots on the right. But the take-home message from those box plots is that all of the methods are sort of about the same in terms of accuracy. In terms of time, there is definitely a difference. So if time here is in this table, and the horizon is the column of the table, low horizons take a long time, and high horizons take much less time. So we get about the same accuracy, but with more replication, we get much quicker turnaround time for our predictions. It's actually an implementation detail. We have some checks in our code. So think about how do we determine what a replicate is. That's something to do with the distance in the input space between those 2 locations. and that's a tolerance like 10 to the minus 4 or something, and horizon -1 doesn't use that tolerance. So it always replicates, almost always replicates. So it's an implementation detail, which I didn't explain. The other two lines on the table are telling you about how many replicates there are. So how many of them are 1 replicate, how many of them are 5 replicates or more. But I don't think we should go through that considering the time. If we look at more than just accuracy, if we do accuracy and predictive uncertainty together, variance, which was not something that our heuristic was directly targeting, we were just doing integrated mean square prediction error. We were not trying to estimate the variance function with our criteria. However, what these results show is that with our lookahead, we do get a better estimate of predictive variance. So that's being shown by score. Higher numbers are better, and some of our horizons drive us to higher scores than others, which means that some of our methods get a better estimate of variance than others. Which methods get a better estimate of variance? The ones that have higher horizon. The ones that encourage more replication. That makes sense. More replication, better ability to separate signal from noise. Better way to estimate the noise. All right, my last example, my basically last slide, is to go back to the assemble to order problem and show you the RMSEs for that one sequentially as we add designs. There is a great diversity in performance in this method. This simulator actually has lower variance than the epidemics one does, but it's a much harder problem. It's a higher dimensional input space, 8 inputs instead of just 2. And in this case, it makes sense to have lower horizon, not higher horizon. So the lowest horizon methods perform best. And our adaptive scheme, which is the yellow one on the right, performs almost as well as the best horizon, which is the lowest horizon. So the adaptive scheme is able to learn that you want less replication. There's still quite a lot of replication going on, but I didn't put that table into the talk. All right, let me wrap up. I think I made it. Let's see. Oh, I did. All right. When the mean and the variance are changing in the input space, it's still possible to get very accurate fits with Gaussian processes. You couple them together, you handle replication in a way that doesn't make any approximations, and you get an efficient method. And you can do a sequential design scheme to learn about the level of replication in a real-time fashion, so you can get more replication in some parts of the input space than others. Intuitively, that's what you would want. If the variance is higher, you'd need more replicates. If the variance is lower, fewer would be okay. We have an R package. Everything that I've just shown you is available in that R package. Everything that involved R code in this talk is fully reproducible. The pictures were generated from the code. And I've been having a lot of fun doing that lately for my talks. Thanks very much for listening. Thanks again for the invitation. There's a lot of sample code in the R package. If you want this talk, I'll send it to you. Yep, just email me.
So the last example is a little bit counterintuitive. You have less variance in this ATO example, but H minus 1 is the best, and H minus 1 prefers a lot of replications, right?
Actually, I didn't show you the numbers, but H minus 1 is not the best. In fact, I think actually this one had smaller averages, and adapt, which automatically chooses the horizon as it's going, is just as good as the best.
But if we just look at the non-adaptive schemes, right? So the H4 prefers more replications than H minus 1. So yeah. So H4 does more replications or less replications?
H4 does more replications.
Okay. And since there's not much variance in the function.
There's not much variance. That's right. Gosh. Okay. Yes. No. But now you have to answer the question. I was going to say no. Sure. If you could have some kind of bake-off or horse race where you could try all your favorite methods and decide which one is best. Now, when are Gaussian processes good? When the input-output relationships are relatively smooth, when they're nonlinear, when there's not too much data so that you can do the calculations. There are some tricks when you have a lot of data. We give one kind of trick. There are some other tricks. Gaussian processes are no panacea, but a lot of problems in engineering and physics and biology are relatively smooth, and it does a great job of capturing those dynamics.
So if you had, you mentioned an inventory type of problem there,
Mm-hmm.
and it seems like there would be seasonal kinds of things. Would you want to build that into your structure?
There's two ways to... Yeah, I think there are two great ways to do that. So whenever you're working with a Gaussian, you have the mean and the variance to work with. So one way would be to use a non-zero mean. My whole talk was with a zero mean. But if you know that things are going up and coming down, and you kind of know how it's doing it, like over time,
Like
then you...
over your period of time.
Yeah, then...
Goes up or down.
Sure. Then just put a sinusoidal basis in there in your mean function and estimate the amplitudes and phases of those sines. That'd be one way. Another way is through the covariance structure. There are covariance structures that are periodic, and you could use a periodic covariance structure and learn its hyperparameters, which would be tantamount to doing the same thing, to learning the amplitude and phases of sinusoids.
So are they distinguishable?
Is one better than the other? Is that what you're asking? There is an equivalence between putting certain things in your covariance and certain things in your mean. There's a one-to-one mapping, so there is, in some sense, no difference. From an inference perspective, it is much easier to learn unknown parameters in the mean than in the covariance structure, mostly because you can write things linearly in the mean, and then you can get closed-form maximum likelihood calculations. So from a statistical inference perspective, the mean is easier. From an equivalence perspective, there's a one-to-one mapping between the two.
Right, let's thank Bobby again.
That's pretty good. Amazing. Good job.
You know what cell site is?
Yeah.
You know how this, I'm not sure how this is.
Oh, okay, so that walkable. All right.
Oh, yeah, yeah.
Okay.